Yes, class. Good evening. Is this audible to you people?
Yes, ma'am. Good evening.
All right. So, who all are there? Hamza, Hibba, Huzaifa, Krishna, Sarah. So, in the last class, we had started with Ampere Circuital Law. We just discussed what was Ampere Circuital Law. So, I'm repeating it again. So, basically, Ampere Circuital Law is what? Line integral of magnetic field. Line integral we mean by B dot dl. Integration of B dot dl, we call it as line integral. So, line integral of magnetic field. This is mu naught times, that is permeability times the current enclosed. So B dot dl is equal to mu naught times the current enclosed. So we'll be using this Ampere Circuital Law in today's class. So that's why just understand this carefully. So you have to choose an Amperian loop. The way we had a Gauss theorem, no, Gauss law was there. So in case of Gauss law, we chose a Gaussian surface. Then we wrote E dot ds is equal to 1 by epsilon naught times the current charge enclosed. Similarly, here you have B dot dl integral, which is instead of 1 by epsilon naught, you have mu naught times. And instead of having the charge enclosed, you have the current enclosed. Now, as I told you earlier also in Gauss theorem when we were doing that, charge enclosed varies. If you have different values of charge enclosed, if different values of charge enclosed are there, then you just have to actually consider what are the charges that are present and residing within the loop. You don't have to consider all the charges that are outside of the loop. Similarly, here also we'll be choosing an Amperian loop and we'll be considering the current that is only enclosed within the loop. Even if it is not given directly to us, we will be calculating somehow whatever is I enclosed. So that will be done with the help of questions. So this much I think we all wrote it. So according to Ampere Circuital Law, the line integral of magnetic field along a closed loop is mu naught times, that is permeability times the total current enclosed by the loop. So B dot dl is what? Line integral of magnetic field, and we had seen till here. Now for the Amperian loop, for choosing Amperian loop, there are certain conditions. You cannot choose Amperian loop directly. You have to have certain conditions for any loop to be called as an Amperian loop. Now Amperian loop. Now, for choosing Amperian loop is easy. First condition is that it should be a closed loop. Let me write the point simultaneously. It should be closed. Because when we apply this law, no, B dot dl, for this, we only use it for the loop which is closed. So that's why the first condition becomes that it should be closed. Now, the second criteria for any loop to be known as an Amperian loop is that it should either be tangential or perpendicular. What? The magnetic field to the loop. So that basically the reason is that the angle becomes 0 degree. And if your angle becomes 0 degree, then cos 0 becomes 1, and you can easily write BDL.
అయ్యో తర్వాత
Krishna.
Yeah, sorry, ma'am.
All right. So for choosing Amperian loop, basically you have to have a loop whose magnetic field is lying perpendicular or tangential. Reason is that when we always write this dot product, so for writing dot product, B dot dl, even if we are writing, so that becomes B dl cos theta. So whatever values of cos are there, whatever values of cos are there, that determines your Ampere Circuital Law. So if it is 90 degree, so B dot dl cos 90, that directly becomes 0. If we write BDL cos 0 degree, then we can have it as BDL. So that's why we choose magnetic field means B, it should be either tangential or perpendicular to the loop. The reason is that angle becomes 0 degree. Theta becomes 0 degree. Yes, so magnetic field should either be tangential or perpendicular to the loop. So theta becomes 0. So see, in this BDL cos theta, here cos 0 degree will become 1 and you can directly use BDL. So that's why we prefer this B dot DL. One more thing is that if your magnetic field is constant, then your integration becomes easy. See, when we were discussing that lesson before potential and capacitance we started, we had discussed integration and differentiation. When we were discussing integration and differentiation, one rule that is common for both of it is that any constant quantity comes out of it. Whatever is the constant quantity, that comes out of it. So here also, if magnetic field is constant, then it will come out and you can directly integrate DL. So on integrating DL, integration of DL you can do. See, we did it. If we had taken a small section of a circle as DL, so if you integrate all the DLs together, that forms a complete circle 2 pi r. And we have been using integral of DL in the derivation of semicircle, for circular arc, for all these we have been using, because we know whatever is the perimeter, circumference portion, that you put it when you integrate it for DL. So that's why we take the magnetic field is uniform or constant throughout the loop. Throughout the loop. The reason is that when you're performing this B dot DL integration, if magnetic field is constant, then only you can write it as B integral of DL. Then only this is possible. Otherwise, how will you integrate magnetic field? So these are the conditions for Amperior loop. Now the first step for application of Ampere Circuital Law, let us just write it for a normal cylindrical wire or circular wire. Let's just derive it for a cylindrical wire, let's say. Let's derive it for a cylindrical wire. Now keep on seeing the steps to perform what? Ampere Circuital Law. In this only keep on seeing all the steps. So step one basically says choose the right Ampere Circuital Amperian loop. So first step is choose Amperian loop. So if we are taking a wire, let's say this is a wire that we are considering. The loop, the Amperian loop, best possible Amperian loop, if you take a circle whose, let's say, radiuses are, whatever be the radius of this cylindrical wire, I am talking about the radius of the Amperian loop. So first focus on the radius of the Amperian loop. This is the first step. And what is an Amperian loop? How to choose it? What should be the criteria that we have discussed? So first choose an Amperian loop. So here we will choose a circular loop of radius r. So we have chosen a circular loop of radius r. Now the second step begins where your Ampere Circuital Law is applied. So second step 2 is application of Ampere Circuital Law. This is application of Ampere's Circuital Law. So Ampere Circuital Law was what? B dot DL, integral of B dot DL is mu naught times the current enclosed. So I think by now all of you must be remembering the definition of Ampere Circuital Law at least. Now see, in this what is happening, I have drawn it thicker, a thicker wire, but actually it's a very thin wire like this. a very thin wire like this in the form of this. So current in this wire also, how is the current flowing? Current is simply flowing like this. So in this wire also, the cylindrical wire, current is actually flowing like this. So this is the current I that is flowing here. Just a normal wire we are considering. Cylindrical wire means normal, these cylindrical wires that we have, any of these wires. All right. Now B dot dl is equal to mu naught times the current enclosed. First, let us solve B dot dl. For B dot dl, what did we say? B integral of dl. Reason, magnetic field is constant, so we have separated magnetic field, and magnetic field has to be constant. Otherwise, our integration becomes difficult. So B dot dl we have done. Mu naught is what? Mu naught is the permeability, and current enclosed, let's say it's a capital I. So this is the application part now of Ampere Circuital Law. Now step 3 is to put in the values of this DL, means how to integrate this. So obviously it's a circular wire. So for circle, it's like I have a very small section DL. And then I have a very small section DL, all these very, very, very small sections. And if I join it completely at the end, what I have a full circle. You have a very small portion. It's like it was a circle initially, and I had taken a very small segment of it. Very small segment I have dropped. So if I join all the tiny segments, what will I get? I'll get the whole complete circle. So this is what it is. So this will become 2 pi r, the circumference of a circle. And with circle, you just have to focus on the Amperian loop. The way we did in Gauss theorem, we only focused on the Gaussian surface. Our target was the radius of the Gaussian surface. Even electric field was calculated with the help of Gaussian surface. So here we have 2 pi r. Now the final answer, you can get B is equal to mu naught I divided by 2 pi r if you put in the values. This is the formula for cylindrical wire as well as these are the steps of Ampere Circuital Law. Now we'll see two cases for cylindrical wire. One is where it is lying inside, means the point is lying inside in a region inside, and then a case where the region is outside. Now in these both of the cases are very important. It's a part of your NCERT question only. And in CBSE 2010 as well as in I think last it came in 2016 also, exact question. So that is very important from your board point of view as well, and obviously entrance point of view, you have to remember the formula. So we'll do that question, but before that, just note it down. Ampere Circuital Law you wrote, so from Amperian loop just write it. All right, Kulsum, fine. We have just discussed Amperian loop, and right now we have just discussed a step. So while copying down, Kulsum, if you are not able to understand any point, ask me again. I'll repeat it.
Okay, ma'am. Thank you.
integral dl. See, integration of dl, if you integrate dl for a circle, dl was a part of the circle, so when we integrate, integration is basically addition, kind of addition you can say in terms of calculus, in layman terms you can say. So basically all the dls got added up and we can write it in terms of 2 pi r. So instead of this dl, I have written 2 pi r. It's basically like b into 2 pi r, that is equal to mu naught I. So from here, B will be equal to mu naught I divided by 2 pi r. Clear, Fatma?
Yes, teacher.
See, here R is the radius of the Amperian loop. A is the radius of the cylinder. See, the question says you have to calculate the magnetic field of a cylindrical wire in region inside, and then you have to calculate in the second part region outside. So let's solve the first part first. I'm drawing it broadly, but it's just thin wire only. I'm drawing the diameter broad, but this is a normal wire only, normal cylindrical wire like this. It's just that we have to calculate I enclosed and see the radius of both the Amperian loop and as well as the wire. So that's I'm just drawing the diameter broadly. Otherwise, cylindrical wire means your normal simple wires of your earphones or any device. All right. So let's say this is the wire. And the radius of this wire is what? Radius of this wire is A. Now I have to consider a region inside. Inside means let's just here. So my Amperian loop will be this. This will be my Amperian loop and the radius will be smaller. Now where the current is flowing in this wire, this wire, in this complete wire, the whole wire. But see, I am considering what? This Amperian loop. So all of my properties, all of the formula will be applicable for this Amperian loop only. I'm not concerned with any part that is outside the Amperian loop. So first step was what? First step was to choose the Amperian loop. So we have chosen the appropriate Amperian loop. The radius of the Amperian loop is R, that is already mentioned in the question, so no need to repeat it. And again, I'm telling you, this question is a part of your NCRT. I think it's just one line more has been included in your NCRT, that to plot the graph. So that we'll also do it right now only. So this is a very important question and it has been repeated in CBSE papers especially. Now see, then what was our step? To apply BDL is equal to mu naught I enclosed. So we have to have all the terms. Now DL, we will be able to do integration of DL. We will do it because it's a circle, so obviously it will again be 2 pi r. Now I enclosed, see, total current is this. So can you tell me, can I take I enclosed as capital I? Yes or no?
Yes, teacher.
I can take. See, in this region only, this is my Amperian loop. So I enclosed will be what? Current that is enclosed within the Amperian loop. So is current I enclosed within the Amperian loop, or some current is here also? Fatma, just try. Some current will be outside the Amperian loop as well or not?
Yes, teacher.
Agreed, all of you? Some current will be outside the Amperian loop because it's a complete wire. It's like if I had this wire with me and I have taken a very, very small section of this wire within. So the whole current is flowing in this complete wire. But which section I'm talking about, where the current is flowing inwards, inside. So I have to calculate that current which is coming only in the part of the Amperian loop. Fine. So I cannot take I enclosed for it. I enclosed means current that is enclosed within the Amperian loop. Right now, total current I is not enclosed within just the Amperian loop of radius R. It is enclosed within the cylindrical wire of radius A. So my task is to find I enclosed. But what is capital I? Let us just define what is capital I so that we know the difference between capital. Why are we not taking capital I? Basically, what is this area? This area is pi a square. So current enclosed in pi a square is, it is what? Current enclosed in pi a square. This is I completely. Now, current that is enclosed within unit length. Yes, Hanifa, what will be the current enclosed within unit length? Current enclosed for pi a square is I. For a single unit length, it will be okay, Hanifa. Okay, fine. Anyone else from the class?
I by pi square.
I by pi a square. See, it's simple unitary method that you have been using. For pi a square, if it is I, for 1 it will be I divided by pi a square. For a unit length means for 1 meter length, it is I by pi a square. And now in which area do we require the current? We require the current only in pi r square. Pi a square was of no use. Pi r square is our concern. So current enclosed within pi r square area, this will be what? Kulsum, can you try? Yes, Kulsum. Okay, Fatma. Fatma, answer.
I by pi r square.
I by pi r square. So see, for 1 meter, okay, I'll tell you. See, for 1 meter, it's I by pi a square. Now, Fatima, tell me, if for 1 meter it is this, for pi r square it will be, pi r square meter it will be?
Pi r square into I
Yes, pi r square into. It shouldn't be unit length. Basically, it should be unit area. Let me change this because length is not, we are taking the area, so it should be area, unit area. All right, Fatima, did it get clear why it will get multiplied?
Yes, teacher.
Because for unit area we have it. So for pi r square, it's simple unitary method the way you do. So it will be pi r square I divided by pi a square. Pi got cancelled. So our I enclosed, this will be I into r square divided by a square. I enclosed was trickier here. Now rest of the question is easy. Everything is easy now. How to perform it? So B will be there, integral of dl will be left, mu naught, and instead of I enclosed we'll write I r square divided by a square. Integration of b dot dl becomes 2 pi r because it's a circular loop. Circle we have considered as the Amperian loop. So it is mu naught I r square divided by a square. 1 r got cancelled. So what was left? So 1 r gets cancelled, and how much is left? B is equal to mu naught I r 2 pi a square. This much is right now left. So this is when interior of the cylindrical wire. Now, if I choose, this was the first part. If I choose the second part, it means exterior to the wire, a point lying outside to it. So if it is lying outside C, this is the wire, cylindrical wire of radius A. Now I have to choose outside, means my Amperian loop will be this. This will be the Amperian loop with radius will be what? Radius is small r. And I current is flowing. Now can anyone calculate and tell what will be I enclosed? All of you calculate and tell me what will be I enclosed right now. Before writing down anything, just calculate in rough and tell me what will be I enclosed for the second part, region outside. I'm waiting for the answers in the chat box right now. Yes, what is current enclosed? Should I call names and ask, or you people are trying right now? Except for Fatima, I haven't received any answer. Sarah, what's your answer? Krishna? Okay, Krishna has answered. Sarah, Kulsum, your answer as well. See, Fatima is right. You have to consider the current that is within the Amperian loop. Now the complete wire is within the Amperian loop. So it means you have to enclose what? The total current is coming. So it will be I. It will be capital I. It won't be same as the first case. In first case, we had the current in a very small portion of Amperian loop. So that's why we had to apply unitary method. In the second case, the whole wire is included within the Amperian loop. So obviously the entire current will be the entire current enclosed, because you can see current enclosed is I. So here in this case, this becomes to this exactly similar to the derivation that we did. This will be mu naught I enclosed. I enclosed here, this is I. So B 2 pi r will be equal to mu naught I, and you get the same question, mu naught I divided by 2 pi r. This way. Now, one more thing that is given in NCERT to plot the graph, and the graph also comes. So you have to remember these two, because these are very important. Now let's plot a graph between the magnetic field B, the y-axis, and the distance, radius on the x-axis. So again, starting from the center, let's say this is the center O. And this, let's say this is the surface R is equal to capital R means the surface of the wire circle, and this is inside the cylinder, and this is outside the cylinder. Radius is A. Now see, this region is what? This region is inside. As you can see, I have divided the graph into two parts. This is one region. This is which region? This is the inside one region, inside. And then this is the region outside. Now we have to plot the graph between B and R. So see, in the first case, or let's say inside. Inside was which one? This was the inside one. B and R. See, what's the relation between B and R? Magnetic field and the radius of Amperian loop.
Directly proportional.
Directly proportional. So it will be what kind of graph? For directly proportional, we have if two quantities are linearly proportional. So what kind of graph we get? We did graphs also. We discussed graph. X is directly proportional to Y. So X versus Y graph looks like it's a straight line. See, if B is directly proportional to R, it will be a straight line, no? Then only as you keep on increasing the value of magnetic field, the value of R will also get increased. So it will be directly proportional. And we had discussed graph. You can just revise it once, because these graphs are basic. You have so many graphs in your syllabus. Otherwise, you'll forget all the graphs. Because many a times you have to remember the graphs with the help of formula only. If you remember the formula, you'll be able to plot the graph by yourselves. Now, outside is what? Now, can you tell me about outside? How are B and R related?
Inversely proportional.
Inversely proportional. So, for outside, it becomes inversely proportional. From here, the nature of the graph changes. This is inversely proportional. So, this graph also, it can come. Only the graph can also come. So remember these two formula for a cylindrical wire. This is included. Rest, now you just have applications of Ampere Circuital Law. That we'll do, but note down this question. And in whichever step you're not able to understand, ask again. I'll repeat the step. See, basically, applications of Ampere Circuital Law include two applications which are included in your syllabus. First one is the case of a solenoid, and similar to solenoid, you have a device known as toroid. So solenoid and then toroid. These are two devices that are included in your syllabus. Now just understand solenoid completely. Toroid has a very slight modification. The questions are same. Even the formula will appear same to you. Now for the solenoid, let's start it for a solenoid. Now, basically understand what is meant by a solenoid. Solenoid is basically number of turns are there of insulated copper wire. Basically, copper wire is there which has insulation linings, and then it is turned into in the form of coils like this. In the form of coils in this way. These coils, and that we call it as a solenoid. 2 minutes. So solenoid is basically wires are there, copper wires that have insulations like this. This is meant by a solenoid like this. This is meant by a solenoid. Now see, in this case, current flows into it and then current appears to come out at the other end. Because it's a wire, it's in the form of circle, so current will appear to go in, then in from the bottom it will appear to come out. This way it will keep on moving. So if a current flows in this direction, this will be the path of current. This way it will keep on repeating. So basically it consists of number of turns of insulated copper Y. All right. Now see, we won't be using this diagram for our derivation because obviously, look at this diagram. Will you be able to even figure out where the magnetic field is going, where the current is flowing? So that's why we'll draw another diagram which has the properties of magnetic field. Means while looking at it directly, you can easily figure it out. Let me show you. See, one end I'm showing where the magnetic field is coming outwards. So that I'm representing with the help of dots. Dots are used to represent magnetic field lines that are outwards. And this is used for inwards. So this will help us to calculate. Now I have to consider for the Amperian loop. I have to consider an Amperian loop for the calculation of Ampere Circuital Law. So the Amperian loop that I have chosen is this. This is a rectangular Amperian loop. Let me name it as A, B, this is C, and this is T. This is the Amperian loop I have chosen. Now this has been divided into 4 segments, 1, 2, 3, and the 4th one. So basically this is the same solenoid. It's just that to diagrammatically, otherwise in the previous one it's difficult to analyze. Now the calculation part. BDL will be what? It will be BDL for the first part from A to B, plus then it will be BDL for the second part from B to C, then B dot DL for the third part from C to D, and then for the 4th part B dot DL, last one is D to A. All these 4 parts, if you solve this part, then what will be left? You just have to equate it with mu naught I. Remember the steps. See, derivation of solenoid, derivation of toroid, both are similar. Just understand solenoid well. We'll do numericals before even moving on to toroid. And we won't do any numerical on toroid. Just focus on solenoid. Then rest of it will be easy. It's just that this diagram looks confusing, but it's the solenoid drawn only. The 2 ends have been represented with the help of dots, which shows current is moving outwards, and then the other one that shows current is moving inwards, like this. In this way. This you can imagine. Now, for each of the part. For the part AB, this is the part AB. Magnetic field means DB. Here it is parallel and uniform. So it will be normal for the first part. This will be what? BDL cos 0 degree because magnetic field is parallel. Now look at this part BC. Here 90 degree is formed because magnetic field, if you look at the angle, here it was 0 degree, understood. But for this part of Amperior loop, this is making an angle of 90 degree. So for even BC and for AD, for both of these, angle is 90 degree. Now, if you open it for BC and for the last one AD, this becomes BDL cos 90 degree. For this also, it becomes BDL cos 90 degree. Now, for the CD part, which angle it is making? It's making angle of 0 degree. That's clear. CD is making an angle of 0 degree. It's parallel. But see, just look at the segment CD. Don't look at any other segment of the Amperian loop. Does CD include any magnetic field in itself? Or is it lying outside the solenoid? Look in the figure.
Outside the solenoid.
Outside the solenoid. So magnetic field is not there. If magnetic field is not there, then obviously B is 0. So B dot DL will obviously be 0. Otherwise, it would be BDL cos 0. That is agreed. But CD, just this segment we are right now considering. No, since there is no magnetic field, this portion will be having 0 magnetic field. So since B is 0, here this becomes 0. Now, BDL, this becomes BL. Length is L, let's say. L is the length of this rectangle. This becomes 0. This is already 0. BDL is 0. B dot DL, what did we get? This is B dot DL integral. We got it as BL. And B into L, this is actually equal to mu naught I. Clear? BDL. Now see one thing. Current is there. Current I is what? Right now, this current. Current I is for single loop. So if n number of turns are there, n is the number of turns. If n number of turns are there, then for a single loop, it was I. So for n number of turns, what will it be? Any guesses?
Ni.
Ni. For one single turn, it was I. So for n turns, it will be Ni. So I enclosed will be right now n into I. So now see what does the formula become? The formula has become BL is equal to mu naught capital Ni. Now let's put the L in the denominator as we are only calculating the magnetic field. We are just calculating magnetic field. So this becomes mu naught Ni divided by L. Now number of turns per unit length. This is what? Number of turns per unit length, N divided by L. This we are, instead of writing it every time, we will write it as what? Small n. So magnetic field becomes mu naught N. Where N is what? N is number of turns per unit length. This is the formula of magnetic field for a long solenoid. Now, what is meant by a long solenoid? Long solenoid means you can look at this wire. Look at this wire. For this wire, if I give you this much length, see, the length is so much and the radius is so small. If I tell you there are so many coils present here, though this is a wire, just example, you can imagine it as a coil. If I tell you that there are coilings of thin wire which are appearing like this, so what will it be? Radius is very small, a very narrow radius is there, while the length is huge. That we call it as a long solenoid, where length is greater than the radius. This is known as long solenoid. And remember, at the ends of the solenoid, the endings of the solenoid, at the ends, this is mu naught Ni divided by 2. Mu naught Ni divided by 2 at the ends. So derivation of at the ends, you don't need to learn. Even the questions at the end do not come in exam. But just for your knowledge, just in case if it comes, keep it in mind that at the ends of long solenoid, it is mu naught Ni divided by 2. Now, one more thing. Remember, I've told you when we were discussing Coulomb's law that absolute permittivity of free space is epsilon naught. But if a medium is changed, we use epsilon, which is relative permeability of free space or for any space or any other medium. Similarly, this is permeability. Permeability for free space is mu naught. For relative permeability for any other medium, if a solenoid is kept in another medium, then it won't be mu naught only. If mu r is the relative permeability, if mu r is the relative permeability, then magnetic field for the solenoid becomes mu naught mu r Ni. Just multiply everything with mu r. Clear? Any doubts in here for the derivation of solenoid? Just ask me. Wherever, while noting it down at each step or any step you're not able to understand, just ask me, just text me in the chat box. I'll see your doubt and I'll read it out and reply. Now, write down the derivations of a solenoid.
Why the second part of the solenoid is not enclosed in the loop?
Second part means we have taken such a case, means CD is above.
Okay.
Krishna? Understood. CD, we have chosen this rectangular portion, which is not completely enclosing. It's a part of derivation only, since it's not a special question, it's just a derivation. So we have to consider only a region and it has to be closed. So we have to complete the CD. So for completion of CD, we have to take such a portion where magnetic field is not there so that our AB doesn't get disturbed. Remember, any point outside the solenoid, magnetic field is 0. So B outside is 0. So that's why in the CD part, magnetic field is not there. You were asking this, Krishna, or anything else?
No, ma'am. I was saying that the below part of the solenoid, ma'am, the down part where uh, the magnetic goes inside, right?
This
Why is it
part.
not enclosed in the loop? Yeah.
This is not included because you just have to include a portion of magnetic field. Right now we are not focused. This is basically current is moving from outwards to inwards. So I enclosed, we are already considering when we are writing I know, that means the total I enclosed. But just for derivation, actually these are dB. Basically this is also dB. But since in the derivation, ultimately magnetic field is constant, so we write it as V. That's why I'm not considering dB. dB is basically what? A small portion of magnetic field. That's why we have considered the Amperian loop in a very small portion. Clear?
Okay, ma'am.
just try the question also. Once you are done with the writing part, then note this question and try it. And all of you, then whoever gets the answer, send me the answer in the chat box. So it says a solenoid coil of 300 turns per meter is carrying a current of 5 amperes. The length of the solenoid is 0.5 meters and it has a radius of 1 centimeter. We have to calculate the magnetic field inside the solenoid. Yes, Kulsum, your answer is right. Leave the answer in terms of pi. No need to solve it further. Just write it in terms of pi. Hanifa, tens powers have not been mentioned. And Fatima, slight error in the answer. Just check your calculations again. I think only Krishna's answer is right. Hanifa's is also right. Hanifa, you have put in the values of pi, no? 3.14, you have kept it, no?
Yes, ma'am.
Let's discuss it now. Sarah, I think it's not correct. No, Sarah, just look again. Hamza, yes, it's right. See, this data, no, the length of it and the radius of it, this has just been mentioned to tell you that it's a long solenoid. Length is what? Length is 0.5 meters and the radius is what? Radius is given as 1 centimeter. So this is given just to tell you that this is a long solenoid. Long solenoid means length is greater than the radius. This shows that it's a long solenoid. Now you see number of turns per unit length is what? Small, and we wrote that is given as 300 turns per meter. This is not even per centimeter, so you don't need to even convert it. This is 300 turns per meter, that is given directly. And current is what? Current is given as 5 amperes. This is turns per meter. And what is left? Mu naught, we write it as 4 pi into 10 to the power minus 7 Tesla meter ampere, this much. So just put it in the formula. B is equal to mu naught Ni. Mu naught is 4 pi into 10 to the power minus 7. N is 300, current is 5. So this becomes what? 12 into 5 is 60. 60 pi. And this becomes what? 10 to the power minus 7 is there. Minus 5 it becomes, no? So that is 6 pi into 10 to the power minus 4 Tesla. Yes. This much will be the magnetic field. Now one more question I'm giving you similar to this only. 3.76 into 10 to the power minus 3. 6 into pi will be what? Something 1.88 something, no? 18. 6 into 3 is 18. So it will be 1.9 something, no? Hamza and Kulsum, I think, Kulsum also. You people are getting 1.9 into 10 to the power minus 3. Is it 6 into pi only after putting it?
Yes, ma'am.
Yes, no? So yes, so when you solve it, no, you will get it as 1.9 into 10 to the power minus 3. Others also check if you people are getting the same answer after multiplying. So I think only 2 students gave it. Kulsum gave it and Hamza gave it. And Krishna's answer was exactly the same. 1.8 into Hanif, I think power will be 10 to the power minus 3. Rest of it, your magnitude also was right. And who else answered? Fatima, it was not. There was just error in the pi, the in front of the pi. You wrote 4 pi, which had to be 6 pi. So I think something must have missed by you. Rest of the things are fine. Now one more question I'm giving similar to it. All of you try it again. Similar question. Everything will be the same. I'm writing it down. Just first copy this upper portion, then I'll write it. Try this. All of you should try this. See, the solution is in front of you. And leave the answer in terms of pi. No need to solve it further. You can do that in the exam. Right now, leave it in terms of pi only, like this, at this level. And send the answers, because this will take more time, no? So that's why. At least for today's class, you can send it. I have received only Krishna's answer. Fatma, Sara, Kulsum, give your answers. Hamza, you also. And Hiba, what about your answer? Last question also, I think you didn't answer. Try this question at least. Others also respond. Krishna, Fatima, and Sarah have answered. Hamza, Hiba, other Fatima, what's your name? Fatima Munir. Your answer, you also try. I'll discuss it after 2 minutes, but at least try. Hamza, you also. Last time your answer was correct, no? Hamza and Kulsum. You also try. Whatever answer you're getting, it submitted, then we'll discuss. No more answers are coming. By the way, I haven't received any single answer. 10 pi into 10 to the power minus 3, pi into 10 to the power minus 3, only 10 to the power minus 3, 6 pi. See, one thing, for those who are getting, this is what? Kulsum, I think you can get the right answer. Just write it properly with the powers of 10 and multiply. Kulsum, I think you can get the right answer. Just do it properly. The powers of 10 and multiply it. Yes, Krishna. Did you understand, Krishna, now? What was the mistake committed earlier?
Yes, ma'am.
Sarah, I think you just read the question again. Sarah, you also can answer it correctly. Because you have done it correctly. One slight error is there, the way Krishna had done it. Read the question carefully. Krishna, what was the mistake?
Ma'am, I ignored the length.
Ignored the length, exactly. See, it's given number of turns only, number of turns per unit length. You do not have that. Look at it in the previous question. That's why I'm asking you to read the question carefully. In the previous question, number of turns per unit length means small n was given to you. We did this derivation. No, that small n is what? Number of turns per unit length. Now in the second case, second example, we have number of turns only. Unit length is not given, so you can calculate small n, number of turns per unit length. Here you have rest of the thing is same. It's a long solenoid. Length is given and radius, length and radius are given just to make a comparison between whether it's a long solenoid or a short solenoid. It's a long solenoid. That is definitely clear with the help of length and the radius. You can compare the ratios of length and radius. That's fine. That's same. But just look at the number of turns. It is given. It is not small n. It is actually capital N. Yes, coach. I think your previous answer was also right. So yes, Sarah. 2 pi. This becomes 2 pi, whatever answers you are getting. Pi into 10 to the power minus 3, that becomes 2 times. Don't ignore number of turns. See, capital N. Capital N is given to you as 500. In the previous case, small n was given. Now you have to calculate number of turns per unit length for small n. That becomes 500 divided by length is 0.5 meters. This much is turns. So on division, this becomes 100. B is what? Mu naught small n into I. You notice 4 pi into 10 to the power minus 7, small n is 10 to the power 3, just calculate it. Now look at the unit. This has become 1000 turns per meter. And current is what? Current is 5. So this becomes 5 into 4 is 20, 20 pi into 10 to the power minus 5, minus 4. So that becomes 2 pi into 10 to the power minus 3 Tesla. Yeah, this was the solution to it. Fatima, did you understand? Any doubt in the calculation? Anyone can ask, any doubts there? And Fatima and Hamza, did you get it?
Yes.
And we just have a very small derivation of toroid. Just note it down. Then we'll end the class. Derivation and questions of toroid are similar to it. Very, very slight difference in the derivation. So do submit your assignments of the week, whatever assignments. I think one assignment must be of Tuesday, and one assignment on solenoid you will get today only. So just do the assignments and try to submit it before the next class so that we can discuss. Now see, toroid is simple. Solenoid, you people have understood, it's a coil basically of copper wire. Toroid is if I just bend the solenoid. Bending of solenoid, this will in the form of a ring basically. Let me write it up then. Understand. I hope you have written. If anyone is writing, then just stop me. Otherwise, I'm scrolling. See, solenoid was a straight long coil. If you bend it, means if you bend it like this was the solenoid. So from one end, current is entering, current is moving like this throughout, and ultimately it will come. So we have just bent it in the form of a circle. So toroid is what? Toroid is bent form of solenoid in the shape of a ring. Now again, we cannot use this diagram for the derivation. Obviously, it is very difficult to understand this. So again these dots represent that current is moving outwards because it's a coil basically, no? And these derivation come in the exam, for the derivation for the solenoid as well as for the toroid. This one also. Then this device is known as toroid. So all the properties will remain the same as discussed in the solenoid. And then cross represents now basically we'll divide it into 3 regions. This is region 1, this is region 2, and this is region 3. Now let's individually solve all the 3 regions, then we'll be able to understand it. Let's talk about region 1. This is region 1. So first step is always to choose an Amperian loop. I have chosen this. So in region 1, let's say the radius of it is R1. So B dot dl integral will be equal to mu naught I. But see, in this first region, magnetic field line is not getting enclosed. So B is 0 directly. Now let's talk about the second region, region 2. This is the second region. So I have to choose an Amperian loop. This is, let's say this is R2. Now here magnetic field lines are definitely getting enclosed. So for region 2, this will be B integral of dl equal to mu naught I. So B into 2 pi R2 will be equal to mu naught I. Clear? So magnetic field, we can get it. Magnetic field will be equal to what? Mu naught I divided by 2 pi R2. Region 2 has been solved. Now we have the third region. Third region is lying outside. Let's choose an Amperian loop. Actually, we don't even need to choose an Amperian. The third region. Directly you can say magnetic field outside the solenoid is what? Magnetic field outside the solenoid is 0. So magnetic field outside the toroid is also 0. So no need to even choose the Amperian loop. Directly write it as 0. In your derivations also in your exam. So in the region 3, magnetic field outside is 0. So B becomes 0. This is B1, this is B2. This is B3. Now net magnetic field will be sum of all these. First and third are 0, so total magnetic field will be the second one. So since we have only single radius, since we have only single magnetic field left at the end, let's not write it as 2 or 3 or 1. Let's directly write it as B. So B becomes what? B becomes, this is equal to mu naught I divided by 2 pi R. R I'm taking. Now again, this is for what? This is current for a single loop. But we know for a toroid, for a solenoid, we don't have a single loop. We have number of turns. So I is current for a single loop, single turn, and obviously n number of turns we have to keep it in mind. So n is the number of turns. So again, I enclosed becomes what? This is I enclosed. So I enclosed becomes what? N into I. So formula will become mu naught Ni divided by 2 pi R. Now n divided by 2 pi R. This is the formula, you will be using this only. But see, n divided by 2 pi R, if you just focus it, n is number of turns. 2 pi R is the circumference of the circle, circumference of the toroid. That is the length of the toroid. The length is in the form of a circle. So this basically, this is what? This is the length of toroid. So this becomes what? Number of turn per unit length. We can write it as small n. So small n is number of turns per unit length. So finally, this will also be V is equal to mu naught. Instead of n divided by 2 pi r, I am writing small n, that is number of turns per unit length, I. Yeah, and the numericals and everything, that will be the same. If number of turns are mentioned to you, then take radius will be given. So take 2 pi r divided and get small n. If number of turns per unit length is mentioned, then directly write it. Yeah. Is this clear to all of you? Yes or no?
Yes, ma'am.
Others? Only Krishna is understood.
Yes, ma'am.
Understood, ma'am.
All. So note it down. At the end, when you people have completed, just text me done. I'll stop it there. So this completes your Ampere Circuital Law. And others, Krishna has done. Others are still writing. All right, those who have completed, you can leave the meeting. Most of you, I think, have completed. So this completes your Ampere Circuital Law. Just revise Ampere Circuital Law. From the next class, we'll be doing magnetic Lorentz force directly. All right, take care. Bye-bye.
Thank you, ma'am.
Thank you.